Hey everyone, welcome to Insights by Rish. Today we are going to implement a deep learning project of bank churn prediction. This is a binary classification project in which we want to predict whether the customer will retain your service or will he leave your service. Now this is a binary classification project which you can implement using various machine learning algorithms like logistic regression, naive-Bayes, support vector machines, etc. But we are going to implement it using the deep learning approach by using TensorFlow and Keras. Now this is the dataset that we have. We have row number, customer ID, surname, credit score, geography, gender, age, tenure, which is in months, balance, number of products, has credit card, is active member or not, estimated salary, and exited. Exited is our target feature which we want to predict, and 1 means the customer is exiting your service, and 0 means the customer is retaining your service, which we want to predict here. This dataset is downloaded from Kaggle and I will provide the link of it in the description box. Now coming back to this, I have loaded my dataset into the Google Colab system by the churn_modeling.csv file, and now we'll start by importing it. So import pandas as PD, and then we will load the dataset into the bank_df variable, which is of data frame data structure. So we will read the CSV file. We need to provide the name of the file with the extension. Let's run this. And we will load the first 5 rows of the dataset using the head function. So this is the dataset that we have, and the exited is the feature that we want to predict. Now by looking at this dataset, we can figure out that we have some unwanted columns here, like row number, customer ID, and surname. We don't require this column for any kind of prediction. So for the first thing that we will do, we will delete the unwanted columns. So let me give the comments as well. So deleting the unwanted columns. So to do that, we will use bank_df.drop method, and we will supply the names of columns that we want to delete. So let's say we want to delete roll number, customer ID, and surname. So I will provide it here. And I will also provide in place is equal to true. If you don't want to provide in place is equal to true, then in that case you can assign the whole this line to a new data frame. But if you don't want to do that, you can just provide it with an attribute of in place is equal to true, which is used to make the changes permanent and not just temporary. Let's run this, and then we will again display the first 5 rows of the dataset. So now the unwanted columns are deleted. The next thing that we will do here, first we will check for the null values. We will use the isAny function. Now every value here is 0, which means we don't have any null values in this particular dataset. So now the next thing that we want to do here, by looking at the dataset, we can say we have some categorical columns here like geography and gender. So now we will convert the categorical columns into the numerical ones. We will start with the gender column. Let us check the unique values from the gender column first. So bank_df, and we will check the unique values for gender column by using the unique function. So we just have 2 unique values, that is female and male, which means we are going to use the label encoder for converting the categorical values of gender column into the numerical ones. If you have more than 2 values, then you can prefer one hot encoding as well. Now here we have just 2, so we will replace it using the label encoder. So we will use from the bank_df. So we will use the replace method here, and we'll provide a dictionary in replace which says that if it is female, then replace it with the value 1, and if the value is male, then replace it with the value 0, and we will again provide in place is equal to true to make the changes permanent. Let's run this, and now we will check the unique values from the bank data frame again. You can see now the values are converted into 1 and 0. This is what we wanted. The next categorical column that we have here is geography. Let us first check the unique values from geography column. So it depends upon the number of unique values that which encoding method that we will use, and as you can see here we have 3 unique values here. France, Spain and Germany. That is, all the users in this particular dataset belongs from either of this one of these three countries. So as we have more than two values here, we will prefer one-hot encoding here, and we will use the pandas get dummies function. First we will provide the data, which will take the name of data frame, which is bankdf, and then the columns that we want to convert. So here we want to convert the geography column into the numerical one, and it is displayed at first. I'm not assigning it to anything, and I'm not even making the changes permanent here. I'm just trying to display the things. Now looking at this, you can say the three new columns of geography France, geography Germany and geography Spain are appended at the end of the data frame, but the problem is that they are containing the values true and false, and these aren't the numerical values. So to convert these values, to convert these trues and false into zeros and ones, we need to convert the data type of this pd.getDummies function explicitly using the asType function to int. Let's display that. And you can see now the values of geography Germany, geography France and geography Spain are in the form of ones and zeros. So you need to explicitly convert the values of pd_getDummies function. Now we will assign it to a new data frame, which we will again name it as bankdf, and let's run this. So let us again display the first 5 rows of the bank data frame. So now this is our new data set, and you can see that it consists of no categorical values anymore. But to confirm again, we will just display the data types of every column explicitly using the dtypes function. Here you can see every column is associated with the integer data type, which means we don't have any categorical column here. So we are successfully done converting the categorical values into the numerical ones. The next thing that we want to do here is, you can see there are some columns which are on a different scale compared to the other columns. There are some columns which are on the scale of zeros and ones, and the columns like credit score, balance and estimated salary are on a different larger scale. So we will perform the data normalization next. And before performing the data normalization, first we will divide our dataset into the input data frame and the target feature. So dividing the dataset, let's consider that capital X is your input data frame, and you want every column into an input data frame except for the exited column, which is your target feature. So you will drop that particular column, which means you are including all other columns here. So you will use the drop method, and you will provide the columns that you want to drop, which is exited, and in the y variable you will store your target feature from the bank data frame, which is exited. Let's run this and let us check the shape of it. So now we are having 10,000 values here and 12 columns. So now we will perform min-max scaling upon this input data frame. Let us once check the names of columns in our input data frame to confirm that there is no exited column here anymore. Okay, so we don't have that column now. So let us perform min-max scaling upon this, and to perform min-max scaling, or we can say it as data normalization, we will use the min-max scaler from sklearn library. So sklearn.preprocessing, we will import min-max scaler, and then we will create an object of min-max scaler. Let us name it as scaler. Now we will use the fit transform method. If you want to do both the things separately, individually, you can do that. You can first use the fit method and then the transform method, but to reduce the time, I am going to do that in one go. So X is our new data frame into which we will store our transform values. So we will use scaler.fit_transform method, which will do both the things in one go, and we will transform our existing X data frame. Now let us display the first 5 rows of the input data frame, which is now scaled. You can see now every column consists of values on a same common scale, which is between 0 to 1. So the scaling of the data normalization is done. Now the next thing that we want to do here is we will perform train test split. So from sklearn.model selection, we will import the train test split module, and then we will say xtrain, xtest, and then ytrain, ytest, and is equal to, we will give the train test split. It will take the input data frame and the target data frame, which is y. Actually, that's not a target data frame, which is a target series or a target feature. It's not a data frame. Input feature is a data frame, x is a data frame, but y isn't. Then we will give the test size, which is 0.2, which means 80% data in the training set and 20% data in the testing set. And at the end, we will give random state is equal to 42. And you can give any value here apart from 42. This is just because you want same rows in the training set and the testing set when you rerun the code. Let's run this. And let us check the shape of xtrain and xtest. Xtrain and xtest. You can see out of 10,000 rows, 8,000 rows are in the training set and 2,000 rows are in the testing set. So we are done with train test split. The next thing that we want to do is we will actually build our model here. So let us write building the model. So to build the model, first we will import the necessary libraries. So we will import TensorFlow as the alias TF, and from TensorFlow we will import Keras. Now we will build our model here. So we will say model is equal to Keras dot sequential, and the S is capital for sequential, and here we will provide our layers. Now the first layer consists of input layer as well as hidden layer. So let's say Keras dot layers dot dense. Dense means basically you are saying that every input neuron is connected to every other output neuron. So you want that every neuron should be connected to each other in the neural network. So that's why you are providing it with the dense feature. If you want to try anything else, you can do that. So firstly, in the initial stage, we will create a simple single layer perceptron, which means it would have just input layer and output layer. So in the input layer, let's say you have shape 12, as we are having 12 columns here. As we are having 12 columns here, so our input shape is 12. And the activation function that we are going to use here is sigmoid. We are doing binary classification, and hence we will use sigmoid activation function, which gives you the value between 0 and 1. And the main thing here before the input shape is what output you want here. Now here your output layer will consist of a single neuron, because that single neuron will provide you either with the value of 0 or 1 or between that, as you are using sigmoid for binary classification. So you will have a single neuron in the output layer. That's it. The next thing that you want to do is, as we are initially creating just a single layer perceptron, so we will have only a one layer there, which is doing both the works of input layer as well as the output layer. And now we will compile it. So we will say that we want to use the Adam optimizer. Currently, Adam is the best optimizer available for any neural network model. If you want, you can try other like stochastic gradient descent, mini-batch gradient descent, adaptive delta, anything else. But actually, Adam is the best one because it does both the work. It smoothens your curve to reach the global minima, as well as it gives you the adaptive learning rate. So next, as you are performing binary classification, the loss function that you will specify is binary cross entropy, which means this binary cross entropy is also called as logistic loss function that you use in logistic regression. And at the end, you want to evaluate your model on the basis of accuracy, and hence you will provide metrics as accuracy. Next, we will use the fit method on our model. So model.fit, you will provide xtrain, your ytrain, and then the number of epochs that you want. So here I will initially provide it with only 100 epochs. And let's run this. It will take some time. So till that time, we will just write the code, the further code that we require. So we want to calculate the loss and accuracy here, which will we will use the model.evaluate method, and we will provide the testing set here, x test and y test, and then we will print the accuracy, and we will multiply it by 100 because we want our accuracy to be displayed in the percentage. So it's currently on 83rd epoch, and as you can see, all the 100 epochs are completed, and at the end of 100th epoch your accuracy is 81%, which is quite good. Now this is not a very complex model, and hence the validation accuracy or on the training set is 81%. This is 81% is basically the accuracy on your training set. Let us evaluate it on the testing set. Let's display this. It will take some time because this particular cell of epoch is still running. Now you can see the accuracy on the testing set is 81% as well. This is because we just created a single layer perceptron here. Now what if we want to create a multi-layer perceptron? We want some hidden layers here. So we can do that. So let us remove this particular line and we will write it again. So keras.layers dot dense, and now the first layer will be the input layer. So input shape, which is 12, that is we are having 12 columns, and hence our input features are 12, and the activation function. Now this is your hidden layer, and hence your activation function here would be ReLU, which is the rectified linear unit. When you are performing binary classification, then in your hidden layers your activation function is ReLU, and your output layer, the activation function is SMOTE. But when you are performing multivariate classification, in that case again your hidden layer consists of ReLU activation function, but your output layer will consist of softmax activation function. Now this is the first hidden layer. Let me name this. This is the hidden layer first. Now how many number of neurons you want in your first hidden layer, it depends upon you. There is no standard way of deciding this parameter. So let us say the input features are 12 and I want 15 neurons in my first hidden layer. So the next thing is, now we want one more layer here. Let's say we want one more hidden layer. We'll again write keras.layers.dense, and every layer would be dense, that is it would be connected to every other neuron, and now it won't consist of any input shape. Now how many neurons you want in your second hidden layer, it again depends upon you. Let's say in the second hidden layer I want 10 neurons, and again the activation function, which would be ReLU. So I will just copy paste it. This was your second hidden layer. This is your hidden layer 2. Now what if I want one more hidden layer, my third hidden layer? So I will again copy it, and this is my third hidden layer. Now in my third hidden layer I want just 5 neurons, and the activation function again would be ReLU. Now that's enough. The last layer I would add off is output layer. So keras.layers.dense, and in the output layer I will have just one single neuron that will provide me an output of either 0 or 1. So activation, here in the output layer the activation function would be SMOTE for binary classification. That's it. So we are done with adding some hidden layers here, and everything else in the compile will remain same. Also if you want, you can increase the number of epochs if you want. And one more thing I can do here, I can specify a batch size here. Now if you know about stochastic gradient descent or mini batch gradient descent, then in mini batch gradient descent basically you create batches of your instances, and you pass each batch in every epoch and iteration. So the same thing that we are doing here. So let's say my batch size, I am saying it should be 50. I'm saying that my batch size should be 50. So every 50 instances would be in a single batch. Let us run this. Again, it will take some time. So we are done with the epochs, and you can see after the 100th epoch, now your accuracy on your training set is 86%, which is drastically grown from 81 to 86. That is, there is 5% increase in our accuracy on training set. let us evaluate it on testing set as well. This particular cell is still running, so we need to wait for some time. And now you can see initially the accuracy was 81%, which increased up to 86%, and this is because we added hidden layers. Hidden layers actually helps your model in learning more and more, but if the hidden layers increase on a large scale, then it will help your model to learn till so much of extent that your model will start memorizing the data, and due to which you will face a problem of overfitting. So first, now that we have evaluated our model, let us do some predictions here. Let us display the first five actual values which are stored in y-test. So these are the first five values which are all zeros. Okay, we want some ones as well. Let us display from 10th instance up to 15th. And you can see the first three instances are 1, which means the customer are leaving your service, and the last two instances are 0, which means customer are retaining your service. Let us check what our model has predicted, because it is giving such good accuracy. Now for prediction, let us store our predictions in pred variable. So model dot predict, and we will predict for x test. Now let us display the value stored in the pred variable from 10 to 15th instance, which are our predicted values. Now you can see the predicted values are in the form of decimals. This is because the sigmoid function gives you the values between 0 to 1 and not just 0 and 1. If you want just 0 and 1 for binary classification, then you can go for binary step activation function, but generally the sigmoid function is preferred over that. Now if you want your decimal values in zeros and ones, you can do one thing. You can create another variable here, which is binary pred, and you can specify a threshold. That is, even if the decimal value exceeds your threshold, then it would be concluded as 1, and if your decimal value is lower than the threshold, then it would be concluded as 0. Let's say if my threshold is 0.5, that is, if my value of pred is greater than 0.5, then it would be considered as 1, and I will provide the type, which is int. And now we will display the binary pred variable. Here you can see now the values are in the form of zeros and ones, and our model has correctly predicted for every instance between 10 to 15. So the prediction is done. Now we will evaluate our model. So from sklearn we will import the confusion matrix, classification report, various evaluation metrics. So from sklearn dot metrics, you will import the classification report first. The classification report is necessary to check the F1 score as well. That is, whether your data set is balanced or imbalanced. Let us print it. And here we will provide the actual values which are stored in y-test and the predicted values which are stored in binary pred. Let us display this. And this is our classification report. One thing you can notice here, the accuracy is 86%, which is quite good, but the F1 score for the class 1 is very low, that is 56%. This is because if you take a closer look at F1 score, the F1 score is quite higher for the class 0, which means the class where people are retaining your service, but it's quite low for the class 1 where the people are leaving your service. And this is because our data set is highly imbalanced. If you just try to check that, initially the name of our data frame was bank df, and from that you will check the value count of exited column. Let us check the value counts. Here you can see that there are total, out of 10,000 instances, 7,963 instances belong to class 0 and 2,037 instances belong to class 1, which is very lower in number as compared to the class 0. And due to this imbalance in our data set, the F1 score for class 1 is very low. Now let us try to improve the F1 score for this by balancing our data set. And to balance our data set, we will use the SMOTE technique, which is a kind of oversampling technique, and we will perform that SMOTE before the min-max scaling function. When we just divide our data set into x and y, after that we will perform the SMOTE. So let us write SMOTE here. Now from imbalance dot oversampling, We will import SMOTE, and now we'll create an object of it where we'll say SMOTE. Now here we will provide it with sampling strategy. That is, you want to oversample what? The majority class or the minority class? So my sampling strategy is minority. I want to oversample my minority class. And let's give x and y. So we will do SMOTE dot fit resample method, and we will provide the existing x and y columns here. Now let us run this. Let us now again check the shape of x. Here you can see initially you had 10,000 rows, but after the SMOTE technique, after the year that you have performed oversampling on your minority class, now you have 15,000 rows. That's because now if I try to just display the value counts of exited column, that is y dot value counts. Now y holds the values for exited. Let's display this. Okay, so value counts. Here you can see now both the instances, or you can say both the classes, have equal number of instances. The class 1 holds 7,963 instances, while the class 0 also holds 7,963 instances, which means we have handled the imbalance in our dataset. Now both the classes are balanced. After that, we will again perform the min-max scaling upon this, and we'll again perform the train test split. And now you can see that 12,000 rows are in the training set and 3,000 rows are in the testing set. We will again build the model and compile it using the same optimizer, the same batch size and epochs. Let's run this. Now again it will take some time. Now as the number of instances have increased in number, that's why the training process will also consume a lot of time as compared to the previous process. Now you can see before performing SMOTE, the accuracy was 86%, which got reduced to 81 now. But that's not our lookout. Though the accuracy got reduced, but the F1 score might have improved. So let us check that. First, let us compute the accuracy on the testing set, which is 79%. So it got reduced a lot. But see, if you are having low accuracy, that's not a problem, because you will try some optimization, regularization techniques in order to improve that. But if your F1 score is low, then that's your problem, because that is your data set is highly imbalanced. Let us again do some predictions. And predictions, I think, are somewhat different here. Let us again print the classification report now. And now you can see the F1 score of class 1 has increased. Initially it was, I don't remember the exact value here, but it was around something 60% or 50%, something like this, which now it is around 80%. So the difference between both F scores of both the classes of 0 and 1 is now very less. So this was our main lookout, that we want to improve the F1 score of both the classes, which means we want to balance our data set. Now that we have balanced our data set, one more thing that we can do here is, now as we are getting the accuracy here of just 79% on our testing set and 81% on our training set, what if you get 100% accuracy on your training set? You might feel that getting 100% accuracy means you are building the best model, but actually that's the more bigger problem, that you are getting 100% accuracy, because that means your model is overfitting. It will just give you 100% accuracy only on the training set, but not on the testing set. So while the training phase, you might come through 100% accuracy, but as your model is overfitting, which means it's not building patterns, it's just memorizing the data. In that case, when you will deploy your model and will test your model on the new incoming data, your model will perform very poorly. So what if you are getting 100% accuracy in this place for the training set? You can try adding some dropout layers. Dropout layers is a kind of regularization technique in deep learning. In machine learning, you have ridge regression, lasso regression techniques for regularization. Here we have dropout layer. So let us try to add a dropout layer. Now good practice is adding dropout layer after every hidden layer, but here as we are having we are not having 100% accuracy, we will just try adding one dropout layer after the first hidden layer. So let us put that keras dot layers dot dropout, and we also need to provide the dropout rate, which is 0.5, 50%. So let us understand what is this dropout rate and what actually this dropout does. So this will show you the image of this available on the Google, and we'll open it in a new tab. Here you can see in this article, here you can see the left side standard neural network. Here every node is connected to every other node because this is a standard neural network that is consisting of dense layers. But it might happen that your model overfits here. So what you do, you provide a dropout rate, which is, let us assume that, which is 50%. So then your model will randomly deactivate 50% of neurons in each layer. So if you take a look at the right diagram, that is after applying the dropout, here you can see the red neurons are the deactivated one, and you have provided the dropout rate of 50%, which is 0.5. And hence from every layer, the layer 1, the second layer and the third layer, the model has randomly deactivated some few neurons. That is, they won't be connected to any other, and by doing this, your model is actually preventing overfitting. That's basically how dropout works. Now coming back to the coding part, now we have added the dropout layer here, and actually the good practice is adding the dropout layer after every other hidden layer, but you just do that when your model is too complex. This is a very simple model, and hence I am just going to show you a single hidden layer. Let's run this again. Now after the 100 epoch, you can see now the accuracy is 75% on the training set. Initially it was something 79% or 80%, which got reduced to 75%. Now our accuracy was initially low, and hence it got to a more lower extent. But when you are getting 100% accuracy in the training set, and when you use the dropout layer, then your model actually performs way more better than the previous one. So now let us again check the accuracy on the testing set. So we are getting 74% accuracy on the testing set, and the accuracy is actually reduced due to the use of dropout layer, because this wasn't the proper model to use the dropout layer on, as this is not overfitting model. But I just shown you how to use the dropout layer when your model is actually overfitting. In that case, you can perform this, and your model's accuracy will be reduced so that your model won't memorize patterns. We will again do the predictions. Now it would include a lot of misclassifications because the accuracy is low. We'll again print the classification report, and you can see not a much difference between the F1 score of both the classes. Now at the end, the last step that we are going to do, we will print the confusion matrix using the Seaborn heat map. So from sklearn.metrics, you will import the confusion matrix, and now let us store the confusion matrix in a variable CF. So confusion matrix, and here you will provide the actual values which are stored in whitetest and the predicted values which are stored in binary pred, and you will also provide normalize is equal to true. Now I will let you know in some few minutes that why we require this. Let's run this. Now we will plot it using the Seaborn heat map. So we will import the Seaborn library first, and we'll print the heat map. We will provide the CF variable into which we have stored our confusion matrix, and we will change the color of our heat map to the blue theme, and we'll also provide anot is equal to true. That is, we want the values to be shown upon the grid. Let's display this. Now one thing you can see here, the value is in a decimal form, which means you can read it. If you don't provide this normalize is equal to true here, then in that case the value will be quite large in a exponential format. Here you can see now. This is not quite a readable format, and hence we need to provide normalize is equal to true. Again, let me display it. So this is the heat map, final heat map, and what it's saying is on the y-axis you have actual values or the actual labels, and on the x-axis you have predicted labels. So it's saying that 67% times it's the case that your actual true label is 0, and your model has also predicted it to be 0, and only 33% times it's happening that actual label is 0, which means the employees are not leaving your service, but your model has predicted 1. And in the label 1 case also, 82% times it's happening that the true label is 1, which means the employees are leaving your service, and your model has also predicted it to be so, but just the 18% times it's happening that true label is 1, but the model is predicting 0. So this was the confusion matrix plotted with the help of Seaborn heat map, and this was a project for bank churn prediction. We were basically studying whether the customer will leave that particular bank or will keep continuing with the same bank. So that's it for the video. Thanks for watching.